Okay, Module 4, Rational Functions. So before we get started, let's just look at the title and see if we can try to understand what the heck we're dealing with. So first off, we see that this says functions, and when it comes to functions, we're thinking of anything that passes the vertical line test. So if I was to take a vertical line and pass it through from left to right, we want to see that the x values do not repeat. So that's how we can tell if something is a function. So that's what that's talking about. The next thing, rational. Rational just means anything that can be written as a fraction. So that means like 2 is a rational number because it could be written as 2 over 1. Obviously 1/2 is a rational number because it is a fraction. 0.5, so that's a decimal, that's 1/2, same type of thing. Okay, so we're looking at decimals, anything like that. So when it's talking about rational functions, we're talking about fraction functions. So that means something that could have let's say an x in the denominator. So if we have 1 over x plus 1, this would be considered a rational function. So maybe let's talk about this just for a second over to the side, because at the bottom there it talked about domain and range, and let's just say that we had y equals 2x. If we were to create a t-chart, what kind of x values can we choose here? I mean, could I choose 1? Yeah, because 2 times 1, that would be 2. So y would be 2. Okay, what about 3? Would 3 work? 2 times 3, that'd be 6. Okay, what about negative 2? Would that work? So negative 2, that'd be negative 4. Okay, what about 0? Would that work? 2 times 0, that would just be 0. So see how we're getting the broad spectrum here of positive numbers, negative numbers, and 0. And I don't think there's any sort of limit when it comes to the x values that we could choose. We just chose 1, we chose 3, we chose negative 2, and we chose 0. So all of these have a value. Is there any x value that we cannot substitute into this equation? And obviously the answer is no, so that means that our domain, okay, the domain here is all real numbers. Okay, now what about y values? As this thing is coming across, so at 1 it's up at 2, at 3 it's up at 6, at negative 2 it's negative 4, okay, 0, 0. So we see that we've got a linear function, and we see that the y values are just going to continue to decrease as we approach negative infinity. Okay, so the range, okay, or the y values are also all real numbers. Okay, so all real numbers for the domain and range. Okay, so now what about something like this? If I had y equals the square root of x. So if we were to start substituting in some values, x values, like let's say 1, the square root of 1 is 1. Okay, and I could start graphing that. So at 1 it's 1. Okay, and then if I do 2, well, we could do that. We would just get a decimal. Okay, so I'm gonna skip ahead to 4 because the square root of 4 is 2. So we could do that. What about 0? Square root of 0? Did I say the square root of 4 is 4? The square root of 4 is 2. Anyways, 0. 0 is 0. The square root of 0 is 0. What about negative 2 or negative 4? Can I take the square root of a negative number? So here we'd have an error. Okay, and the reason why we'd have an error is because our domain is restricted to no negative numbers whatsoever. So it's almost like there's this invisible barrier, right, that this isn't going to pass, and it's never going to cross or pass 0. So this is what a radical function will look like. Okay, so let's go back to our rational function, the one that I drew up over here. Is there anything that we couldn't substitute inside here? Yeah, see, our x could never be negative 1. Okay, so we have a restriction here. We have a problem. We have an issue. Okay, if we substitute in negative 1, then our denominator would be 0, which would cause a domain error. Okay, so that's one thing to consider. Another thing to consider also is that when it comes to a rational function, if I have x plus 1 up top and an x like this and an x on the bottom, okay, we see that x cannot equal 0, okay, because we can't have 0 in the denominator, but we also see that these x's could divide out. So it'd still be a function, but the function would then look like this, x plus 1. And we know that this is a linear equation. So as we go to graph this, we know that it's going to cross right here, and then our slope is up 1 over 1. So as we go up 1 over 1, up 1 over 1, our line looks something like this. But we have an issue basically, okay? Because the original blue problem here has an x in the denominator, and we realize that x could not be 0. So whenever it divides out here, okay, we don't have an asymptote, but instead we have a hole. Okay, so the line is going to be going, and then right when it gets to 0, there's going to be this open hole, okay, where it's not defined there because it's a domain error. Okay, so this is considered a hole, and then sometimes we have asymptotes. So here's the rule. Oh, actually, let's go back up. Let's just write it right here. Okay, so a vertical asymptote is a domain error. Okay, domain error in denominator. Okay, so in the denominator. Okay. So a vertical asymptote is a domain error in the denominator. So right here, this would be a vertical asymptote. Okay, and then a hole is when it cancels or divides. Okay, so it's an error that divides with numerator, or the top. All right, so let's just try this out. Okay. So if I have y equals x plus 1, x minus 2 divided by x plus 3, x plus 1. Okay, so looking at the denominator, we could say that x cannot equal -3 and -1. Okay, those are the restrictions on our denominator for this rational function. However, since the x plus 1 cancels out with this x plus 1, this is going to be the vertical asymptote, and then this will be the hole. Okie dokie? All right, let's continue with this. So number 1, it says a table of values was created for the following system. Now, we have to remember that when it comes to a system, the solution to a system is a point, an xy of intersection. Okay, so basically it's an ordered pair that they have in common. So let's say that you and your friends want to go out to eat. Okay, if you guys want to go out to eat, let's say that you like McDonald's and you like Carl's, and then your other friends, they like I don't know, they like Jack in the Box and McDonald's. It's like, where are you guys going to go out to eat? Okay, wherever you have whoever likes the same thing, that's the place that you guys are going to be going out to eat. Okay, so in short, we have a table of values here where we have the y values for the f function and the y values for the g function, and so you're looking for ordered pairs, okay, that they have in common. So glancing at this table, we could see that we've got a couple locations. First off, right here, this as an ordered pair would be at -3, 0, and then we also have one down here, and then we also have one right below that. Okay, so here's the situation basically. We have a linear equation, and then up here we have a cubic. So we have a cubic function, and then we have a linear function cutting across. Okay, so we can see that the point of intersection, those are going to be the solutions to this system. Make sense? All right, next. Here it says find an expression that's equivalent to. So we're going to just go ahead and divide. You could use long division, but I'm going to use synthetic division. I'm going to take the 0 of the denominator, which is this guy right here. And then notice I put a 0 right here, and it's red because you don't see that we have an x squared term, so we have to put a 0 placeholder. So I went ahead and did that. Bring down the 1, gets a free pass. And then 3 times 1, that's going to be 3. And then this simplifies to -2. Multiply 3 times -2. Simplify, multiply, simplify, multiply. And so now we have a remainder of -46. And I want you guys to consider if we were just to have a fraction that you guys are familiar with. Okay, let's say we had 21 divided by 4. Okay, an equivalent way of writing this improper fraction is we would just divide. We'd say 4 goes into 21 5 times. Okay, that's the quotient. And then whatever the remainder was, which in this case is 1, we would have that over our divisor, which is 4. Okay, so an equivalent way of writing 21 over 4 is 5 1/4. Okay, so this right here, let me get this out of the way. We have a remainder of -46. So I'm going to write down what the quotient is, and then put negative 46 over what we divided by, which is x minus 3. Okay, next it says solve the following equation for x. So we know how to do this. We're just going to get x by itself first by subtracting 3 from both sides. And then to undo a radical, we have to square both sides. And so I'm going to move this over here. So we have 4, and then the radical is gone, and we have 8x minus 4. Add 4 to both sides. That gives us 8. Divide both sides by 8, and we get x equals 1. Now I just wanted to check our answers, and we know how to do this. We take the original problem, and we substitute back in the 1. So if I put back the 1 and we multiply, that'll be 8. Okay, so 8 minus 4 is 4. The square root of 4 is 2. And of course, 2 plus 3 equals 1. Wait a second here. Did we do this right? I mean, we did all the math right? Over here, it's like, this is the PowerPoint. It's got to be right. Okay, so what happened? So something happened here all the way back at this stage right here. Look at this. When we started to solve this equation, we see a radical equivalent to a negative number. Okay, so this is whenever we have some sort of an issue, okay? Because no matter what we do from here on, okay, it's going to be like we're entering into la la land. Okay, so this solution of x equals 1 is called an extraneous solution. Okay, and the reason why is because we can't have a radical equaling a negative. So here, since it's not a solution, we would just say no solution. Okay, so why don't you try number 4, see if you guys get a solution. Well, we could clearly see that if we added the 1 over, we'd be okay. We wouldn't have a radical equal to a negative, so we could finish solving, and you should have got x equals negative 4. Okay, number 5, it says compare and contrast the following functions and name the points of intersection. So I would just graph both of them, and I see that one of the points is 5, 4, and then another point is an ugly guy. But anyways, you're just going to identify the points of intersection by creating a t-chart and substituting in values. All right, next it says find the difference. Here we have to come up with an LCD. Okay, so the LCD between 5 and x plus 1 is going to be 5 times x plus 1 because the two denominators are different. So that means we're going to multiply the top of this fraction by 5 and the top of this fraction over here by x plus 1. Okay, and then after you subtract, you should get this. Okay, number 7, it says a student claims that for some polynomials, the rational expression blah, blah, blah can be expressed like this. So it's saying quotient plus the remainder over the divisor, okay, where q of x is a polynomial. So does the polynomial, and it gives a polynomial, support the student's claim? So basically what he's trying to say is that if you were to divide x minus 2 into this polynomial right here, he thinks that the remainder is going to be 3. So let's just check it. We'll use synthetic division. We're going to take the 0 of the denominator here, x minus 2, and then go ahead and put that in. We got all the coefficients of our polynomial, and then we're just going to use synthetic division. All right, and our remainder looks like it's 3. So since it's 3, that's what he got. So does it support? Yeah. Okay, next one it says, what is the sum? So we're going to be adding these two things. So the denominators, since they're different, we're just going to be multiplying these two denominators together. So x plus 11 times x plus 4. Okay, and then we had to multiply this numerator by x plus 4, so that's x plus 4. And then I had to multiply this numerator over here by x plus 11. Now we just combine the like terms up top. So we got 2x plus 15. There's nothing that we can divide out. We can't divide out these x's. Okay, it has to be multiplication. So then that would be your answer. Okay, so we have radicals again. So I just wanted to talk again about the extraneous solutions. So listen, an extraneous solution can happen if, number 1, we have a radical that's equal to a negative number as we're solving. So right here we know we can kind of stop and say, okay, we're gonna end up with some solutions that really don't work. Okay? Now another time that this can happen is if we have a variable. So x is over here underneath the radical, and then we also have a variable on this side. So for example, like letter D and E, when we solve these, we have a variable on the other side of the radical. So what can happen here, let's say that if x, in this case, x equaled 10, if we substituted 10 back into this, okay, do you see how 10 minus 12 would give us a negative 2? So we'd have a radical equivalent to a negative number, which goes back to this one right here. So you'd have to check your answers for these two scenarios. If a radical is equal to a negative, or if you have a radical that's equal and there's an x on the other side. So just solving this, we're going to take the square, we're going to square both sides, and you get 25 and then divide by 4. Over here, we're going to take a square both sides. You get a big, huge number divided by 3, and then simplify. Over here, we're going to square both sides, and I ended up with 1/4. And now this one I wanted to go ahead and do with you guys. The square root of x, and over here we have to square this. So this means that this is x minus 12 times x minus 12. Okay? So I have x times this trinomial right here. I just did x minus 12 times x minus 12. That's how I got that. So since it's a degree of 2, it's a quadratic, we want to basically set this equal to 0. So we're going to subtract the x over, and that'll make that a negative 25x. And now we're going to just factor. Okay, so what are factors of 144? That would also give us negative 25. So since this is positive, that means that both of the numbers have to be negative. And so I get x minus 9 and x minus 25. And then from here, we find the solution. So set each of these equal to 0, so we get positive 9 and 25. Now, if we were to take these and substitute it back into the equation, we have to check to see if we're going to end up with an extraneous solution. So I'm going to go with 9. If I put 9 right here, what's the square root of 9? 3. Okay, what's 9 minus 12? That would be negative 3. Do you see how that's an issue? That does not equal. Okay, so we can throw out 9 as being an extraneous solution, and 25, I know 25 will work because 25 is going to beat out that 12. Okay, so 9 is an extraneous solution, 25 is the solution. So if the question asks what are the solutions, then you would just put 25. If it asked what is the extraneous solution, you would just put the 9. All right, why don't you guys try this one? Square both sides, and then you have to use the quadratic formula, and you get x equals 3 plus or minus 33 divided by 2. Good job.